In this video, we're going to talk about the accumulation of change. So here are the things we've seen in our previous videos. If you take the integral, that's the area under the curve. And we saw the integral is kind of the reverse of the derivative. So in our very first video in this unit, we saw that if you take the area under velocity, you got how far you traveled. So we had some velocity function, we got 155 miles, which is how far I travel from the start to the finish. In other words, that's how much my position changed. So it's not telling me my actual position, but it's telling me the change in my position. All right, so that's the important thing. This area under the curve tells you about the change. All right, so the following formula is going to kind of distill that into a formula, but it's very important to calculus. I will learn more about why it's true and how it's going to be useful later, but I want to introduce it now. So it'll kind of pop up randomly, and it's just useful to know this formula. And this is what it looks like. So this is called the accumulation of change formula. So what's happening? I'm starting at my starting point. And again, using our straight line motion stuff, this would be like the position at time 2 or something like that. And I'm going to end up at my ending point, and this would be, let's say, the position at time 4. Again, these are just numbers I'm making up as I go. All right. So how do I get from my position at time 2 to my position at time 4? I can use the area under the velocity function, because that velocity area gives me how far I traveled. So this would be 2 to 4 v of t dt, something like this. All right, so if I start at my starting position, I add the area under velocity, I get to my ending position. All right, this is the essence of the accumulation of change formula. And just in general, it doesn't have to be position and velocity. It can be any function and its derivatives, right? So the derivative of velocity is position. So if I add the area under the derivative, that gives me how much I've changed from 2 points in my function. All right, so we'll have to learn a little bit more before we can do really broad examples, but these are some basic examples. All right, if I know that f of 0 is -3, how can I find f of 2 given this information? Well, if I want to find f of 2, I know it's equal to f of 0 plus the integral from 0 to 2 of the derivative of my function. This is one of the most common mistakes when you're using the accumulation of change formula. You're going between points on your original function, but you're using the area of the derivative. And these things we know based on what's given to us. F of 0 is -3, so we're starting at -3. The area from 0 to 2 is 5, so we're ending at 2. All right, so you can think about this position, you're -3 units to the left. Your velocity tells you in that amount of time you've moved 5 units to the right, and that's going to put you at 2. All right, so that's what the basics of the accumulation of change formula is. All right, same thing. You can try this on your own. All right, pause the video. You should be able to quickly answer this one. Now we're trying to find f of 3. We're starting at f of 0. We add the area under its derivative from 0 to 3. Again, it always has to be the starting point where we started and the ending point. Those are the same values that go here. And we're starting at -3. And we're going 8 units in that amount of time, which means we finish at 5. Right? Position 5, again, whatever unit that is. All right, here we're starting at 0, and we're trying to get to 5. So f of 5 is f of 0 plus 0 to 5, f of x, f prime of x. Again, make sure you don't forget to use the area under the derivative. And we're trying to find f of 5. We know f of 0 is 4. But if you look at what we're given, we're not given anything about 0 to 5. All right, so how can we figure out this answer if we don't have 0 to 5? Well, 0 to 5, all right, this thing here is an area from 0 to 5. Let's just say the area looks something like this. And we don't know what that area is because it's not given to us over here. What we can do is we can break this area up into smaller pieces. So I can break up my area kind of in the middle, and I can have the green area and the yellow area. If I add those two things together, of course, I get the full blue area. And what's the green area? The green area is from 0 to 3. And the yellow area is from 3 to 5. All right, so this is an important concept with areas is we can break up them into smaller pieces, and the 0 to 3 part is 8. The 3 to 5 part is -4, and our final answer is 8. All right, so this is just introducing the concept that instead of finding one big area all at once, we can break it up into 2 small areas or multiple smaller areas, and our notation will look like this. So we'll do the area from 0 to 3, and the area from 3 to 5. That's obviously the same as the area from just straight from 0 to 5. All right, so here's one for you to try on your own. You know f of 3, you want to find f of 5. All right, go ahead, pause the video real quick, and do that one on your own. I'll show you the answer in 3, 2, 1. All right, and you should get 6 for your final answer, and you can see the work there. I say important points for this lesson. All right, make sure you memorize this accumulation to change formula. So it's f of b equals f of a plus the integral from a to b, f prime of x dx. And again, the basic idea is you're getting from one point on your original function to another point on your original function by adding the area under the derivative. And it's useful to think about position. You're getting from your starting position to your ending position by adding the area under velocity. All right, also very important, make sure you remember that it's the derivative in that integral, not the original function. And we're going to use this formula more as the year progresses, especially once we start doing application problems with all the stuff we're learning in the fall.